SwayamPrabha. Digital India. Educated India.
Analysis of inorganic pollutants, lecture number 26. Let us now try to see how these inorganic pollutants are analyzed in the textile effluent. In textile effluent, the measurement of inorganic pollutants is crucial for assessing environmental impact and ensuring compliance with regulation. Here are some common methods for measuring inorganic pollutants in textile effluent. In the previous lecture, we have seen how the organic pollutants were analyzed, and in this lecture we will be concentrating on the analysis of inorganic pollutants. pH measurement. pH indicates the acidity or the alkalinity of the effluent. Textile processes often involve chemicals that can alter pH, leading to environmental concern if not properly controlled. Total dissolved solid, that is TDS. TDS measures the total concentration of inorganic salts, metals and other dissolved substances in the effluent. High TDS value or levels can indicate pollution and potential harm to aquatic life. Heavy metal analysis, and this we had covered in one of the earlier lecture, but we will look here once again in order to understand how these are analyzed. Heavy metals such as lead, cadmium, chromium and mercury are common pollutants in textile effluent due to their use of metal based dyes and other chemicals. Various analytical techniques such as atomic absorption spectroscopy AAS or inductively coupled plasma mass spectrometry ICP-MS or inductively coupled plasma optical emission spectroscopy, that is ICP-OES, are employed for their detection and quantification. Chloride and sulphate. Chloride and sulphate are often present in textile effluent as a result of dyeing and finishing processes. Their concentrations are measured to assess the impact of water quality and the environment. Ammonia and nitrate levels. Ammonia and nitrate are common nitrogen containing pollutants in textile effluent originating from processes such as dyeing and printing. They can lead to eutrophication and harm aquatic ecosystem. Various methods like spectrophotometry and ion chromatography are used for their analysis. Phosphate measurement. Phosphates are used in certain textile processes and their discharge into the water bodies can lead to nutrient enrichment, causing algal blooms and oxygen depletion. Phosphate levels are typically measured using colorimetric methods or ion chromatography. So, each method how they have to be analyzed and each ingredient of the textile effluent falling in the category of inorganic pollutants are described here. Moving on, total suspended solids TSS. The measurement of TSS can be assessed by the measuring of the amount of solid particles suspended in the effluent. These solids can include inorganic materials such as clay, silt and metal oxide, which can impact water quality and aquatic habitats. So, we have covered TSS, but here we are looking from the inorganic pollutant perspective. Cyanide analysis. Cyanide compounds may be present in textile effluent due to their use in dyeing and finishing processes. They are highly toxic and regulated strictly. Analytical techniques such as calorimetry and titration can be used for the analysis of cyanide and their detection. Anion and cation analysis. Ion chromatography is commonly employed to determine the concentrations of various anions such as chloride, sulphate, nitrate and cations such as sodium, potassium, calcium etc. present in the textile effluent. These methods help in assessing the level of contamination and ensuring compliance with the environmental regulations aimed at protecting water resources and ecosystem from the adverse effect of textile industry effluents. Now, let us look at it one by one. How is TDS measured? Total dissolved solid TDS is measured in textile effluent and it is essential for assessing water quality and environmental impact. Here is an overview of how TDS is typically measured in textile effluent. Sampling. Before measurement, representative sample of textile effluent need to be collected. Sampling should be conducted following appropriate protocols to ensure accuracy and representativeness of the collected sample. This means that the sample should be very homogeneous and should be mixed well properly, so that it does not have any kind of difference from the collection or sampling point of view. So, there are sampling protocols which need to be strictly followed. Filtration, which is optional. Depending on the specific requirement of the analysis, the effluent sample may need to be filtered to remove suspended solids. TDS measurements typically focuses on dissolved solids. So, filtration can help isolate the dissolved fraction. So, any supernatant solids should be removed when we are analyzing TDS. Evaporation and gravimetric analysis. One of the traditional methods for TDS measurement involves evaporating a known volume of the effluent sample to dryness and then weighing the residue. The weight of the residue represents the total dissolved solids present in the sample. This method is known as gravimetric method. There is another method which is called conductivity method, and there the conductivity measurements are done. Another common method for TDS measurement is based on the electrical conductivity of the effluent sample. Since dissolved solids in water contribute to its conductivity, the conductivity of the effluent can be correlated with its TDS concentration. A conductivity meter is used to measure the electrical conductivity of the sample, and the TDS concentration is estimated using a conversion factor or equation provided by the instruments manufacturer or based on calibration with standard solution. So, it is a very straightforward analysis using a conductometer, and it is correlated with the presence of the TDS or the dissolved solids in the solution. TDS meter. TDS meter are specialized instruments designed to directly measure the TDS concentrations in a liquid sample. These meters typically operate based on conductivity or optical methods to provide quick and convenient TDS readings. So, these are very smart instruments which give very accurate answers or analysis. They may require calibration with standard solutions before use to ensure accurate measurements. So, as I had mentioned earlier also, all these equipments need to be calibrated from time to time. Titration method. In some cases, TDS in textile effluent can be measured using titration method. For example, chloride can be titrated with silver nitrate solution and the TDS concentration can be calculated based on the volume of the titrant required to reach the end point. And so, we all know how titrations are done. There is an end point, and to reach that end point how much of the volume of the solution is required, there is an equation for calculation. Quality control and calibration. Regardless of method used, proper quality control procedures should be followed, including calibration of instruments and periodic validation of results through replicate analysis, preferably triplicate, or comparison with reference standards. So, what happens is that if the machine is calibrated, then we expect the correct answer. Suppose if the machine is not calibrated and has not been calibrated for a long time, then we are not sure whether it is working properly or not, because after all it is a machine and we cannot be 100% sure that all the time the machine will perform in the similar manner. But by periodic calibration we can be assured, because the reference standards, if they give correct value, the unknown sample also will give correct value. By employing these methods, textile industry can accurately measure TDS levels in their effluent, allowing them to monitor environment impact, comply with regulations and implement appropriate treatment measures to mitigate pollution. Measurement of heavy metals. Although we had covered this, but we will re-look at it from the inorganic pollutants point of view, as I said a while ago. The measurement of heavy metals in textile effluent is crucial due to their potential toxicity and environmental impact. The most common methods used in the measurement of heavy metal in textile effluent are atomic absorption spectroscopy, that is AAS, and inductively coupled plasma mass spectrometry, which is ICP-MS. AAS is a widely used technique for the analysis of heavy metals in water samples, including textile effluent. AAS measures the absorption of light by free atoms in the gaseous state. The concentration of the heavy metal is determined by measuring the absorption of light at a specific wavelength. A calibration curve using standard solutions of known concentration is typically employed for quantification. And here let me add that hollow cathode lamp of that element has to be used each time. The machine is calibrated with copper lamp and copper solution, and then subsequently one by one the hollow cathode lamps are changed and other metals can be analyzed. Inductively coupled plasma with mass spectrometry, ICP-MS. ICP-MS is a highly sensitive and versatile technique used for the simultaneous determination of multiple heavy metals in complex samples like textile effluent. It involves ionizing the sample using an inductively coupled plasma source and then analyzing the mass to charge ratio of the ions generated. Like AAS, calibration and standard solution are necessary for quantification, but the beauty of ICP-MS is that there is simultaneous determination of multiple metals, provided we choose the right wavelengths for each one of them and the wavelengths are not interfering. Inductively coupled plasma optical emission spectroscopy, ICP-OES. Similar to ICP-MS, ICP-OES also utilizes an inductively coupled plasma source for ionization. However, instead of measuring mass to charge ratio, it measures the emission of light at specific wavelength corresponding to elements of interest. Calibration and standard solution are required for quantification. Voltammetry. Voltammetry techniques such as differential pulse voltammetry, DPV, or stripping voltammetry can be used for the detection and quantification of heavy metals in textile effluent. These techniques involve applying a potential to an electrode immersed in the sample and measuring the result current, which is proportional to the concentration of the analyte. So, here it is by using a voltmeter that the current is measured and that is directly proportional to the analyte that is present in the medium. X-ray fluorescence, XRF. This is a new technique, new learning. XRF is a non-destructive technique that can analyze the elemental composition of the sample, including heavy metals, by measuring the characteristic fluorescent X-rays emitted when the sample is irradiated with X-rays. XRF is suitable for solid and liquid samples, including textile effluent. So, this is a new technique, and here the characteristic fluorescent X-ray will emit certain rays and those rays are then detected. Colorimetric method, as the name suggests, colorimetry means color related. It involves the formation of colored complex between the heavy metal and specific reagent. Some reagent of choice can form a colored solution and that color measurement is directly reflecting the concentration of that metal. The intensity of color produced is proportional to the concentration of the metal ion in the sample. Colorimetry methods are often used for rapid screening or as a preliminary step before more quantitative analysis using instrumental methods can be done. For example, chromium 6 can be analyzed by using DPC, which is the reagent. When the DPC solution is added, then what happens is that it forms pink colored solution. Now, the intensity of this pink color solution is directly proportional to the chrome 6 that is present in the medium. Sample preparation. Prior to analysis, sample preparation techniques such as filtration, digestion and extraction may be necessary to isolate and concentrate the heavy metals from the matrix of the textile effluent, especially if the concentrations are low. Now, let me tell you that the textile effluent matrix is very complex, and all these inorganic, organic pollutants are all present together. So, sometimes it becomes mandatory to filter the sample or digest the sample or extract the sample, and therefore, sample preparation becomes mandatory. It is important to choose the appropriate method based on factors such as the target analyte, required sensitivity, sample matrix and available resource. Quality control measures including calibration with certified reference material and participation in proficiency testing programs should be implemented to ensure the accuracy and reliability of results. This means that the same sample should be sent to 2 or more other laboratories, and then the results of all the 3 laboratories should be correlated. This is called participation in proficiency testing program. So, by doing so, we become doubly sure that the results are correct. Now, let us see how sulphate and chloride are analyzed in textile effluent. Analyzing chloride and sulphate content in textile effluent is crucial for understanding their environmental impact and potential harm to the aquatic ecosystems. Here is a breakdown of how such analysis might be conducted. Sample collection. The first step involves collecting representative samples of textile effluent. Samples should be collected at various points in effluent discharge process to account for any variation in concentration. So, sampling should be done from several points so that there is a uniformity in the sample collection. Preparation. Once collected, the sample needs to be prepared for analysis. This typically involves filtration to remove any particulate matter that could interfere in the analysis. Analytical technique. Ion chromatography. This technique separates ion based on their charge. Chloride and sulphate ions can be detected and quantified using ion chromatography. Titration. Chloride content can also be determined through titration, where a known concentration of silver nitrate solution is added to the sample until all chloride ions have reacted, and this method we learnt about it a while ago. Gravimetric analysis. Sulphate content can be determined through gravimetric analysis, where sulphate ions are precipitated as barium sulphate and then weighed out. Calorimetric method. Calorimetric methods involve the use of specific reagents that react with chloride or sulphate to produce a color change, which can be quantified spectrophotometrically. Quality control. It is essential to include appropriate quality control measures such as using certified reference material and running blank samples to ensure the accuracy and reliability of these results. Time and again I have been emphasizing that the machines need to be calibrated periodically. Data analysis. Once the analysis is complete, the data needs to be interpreted. The concentration of chloride and sulphate ions are typically reported in units such as milligram per liter or ppm. These results can then be compared to relevant regulatory standards or guidelines to assess compliance. Interpretation and reporting. The final step involves interpreting the result in the context of environmental impact, looking at what is the seriousness, how much of chloride can cause environmental impact or how much of sulphate can cause environmental impact is what is the main interpretation. High levels of chloride and sulphate ions in textile effluent can contribute to water pollution, affecting aquatic life and ecosystems. This finding should be reported comprehensively, including any recommendations for mitigation or reducing the impact of these pollutants. It means that if these levels are high and they are beyond the stipulated values as given by the regulatory authorities, then it is an alarming situation, and therefore, the mitigation plan should be planned out according to the levels which are reported. Regulatory compliance. Depending on the jurisdiction, textile manufacturers may be subject to regulations governing the discharge of chloride and sulphate ions into water bodies. Any non-compliance with these regulations would need to be addressed appropriately. Overall, the analysis of chloride and sulphate ion in textile effluent may play a crucial role in environmental monitoring and ensuring sustainability of textile manufacturing processes. Now, let us see how ammonia and nitrate levels are analyzed in textile effluent. Analyzing ammonia and nitrate levels in textile effluent is essential for assessing the environmental impact of textile manufacturing processes, particularly concerning eutrophication and toxicity to aquatic organisms. Here is how such analysis may be conducted. Sample collection. Similar to chloride and sulphate analysis, representative samples of textile effluent need to be collected. Samples should be taken from different points in the effluent discharge process to capture any variation in the concentration. Sample preservation. Since ammonia can be volatile and nitrate can be susceptible to microbial degradation, it is essential to preserve the samples properly to prevent any changes in concentration before analysis, and if the analysis is delayed, then it should be definitely preserved. This typically involves acidification for nitrate preservation and cooling or fixing the pH for ammonia preservation. So, there are ways to preserve. If it is for the analysis of nitrate, then it is acidified, the solution is acidified. If it is a matter of fixing the ammonia, then the pH is adjusted. Ammonia analysis. Nestlerization method. This calorimetric method involves the reaction of ammonia with Nestler's reagent to form a yellow brown complex, the intensity of which is proportional to the ammonia concentration. Ion selective electrode ISE, ammonia specific electrodes can also be used for direct measurements of ammonia concentration. Nitrate analysis, cadmium reduction method. In this method, nitrate ion are reduced to nitrite by cadmium, and then the nitrite ions are measured calorimetric using Grease reagent. Ion chromatography. Nitrate ions can be quantified using ion chromatography, and this we learned a while ago while we were understanding ion chromatography method. Quality control. As with chloride and sulphate analysis, appropriate quality control measures should be implemented, including the use of certified reference materials and blank samples. Data analysis. The concentration of ammonia and nitrate are typically reported in units such as milligram per liter or ppm. These results can be compared to relevant regulatory standards or guidelines to assess compliance. Interpretation and reporting. High levels of ammonia and nitrate in textile effluent can lead to eutrophication of water bodies, harmful algal blooms and adverse effects on aquatic ecosystems. The findings should be interpreted in the context of potential environmental impact, and recommendations for mitigation or treatment may be included in the report. If the values are high, then this is of course necessary, but if they are within the stipulated level, then there is no recommendation required to be given specifically. Regulatory compliance. Textile manufacturers may be subject to regulation governing the discharge of ammonia and nitrate into water bodies. Compliance with these regulations is essential to minimize environmental harm. Overall, the analysis of ammonia and nitrate levels in textile effluent is vital for environmental monitoring and ensuring the sustainability of textile manufacturing processes. Implementing effective wastewater treatment technologies can help mitigate the release of these pollutants in the environment. Now, let us see how phosphate is analyzed in textile effluent. Analyzing phosphate levels in textile effluent is crucial due to the potential environmental impact of phosphates on water bodies, particularly in terms of eutrophication and aquatic eco-life health. Here is a step-by-step guide on how such analysis must be conducted. Sample collection. Start by collecting representative sample of textile effluent, and this we have learned. Even in every case, the sample should be representative. That means, it should come from each of these processes and mixed together. Ensure sample are taken from different points in the effluent discharge process to capture any variation in phosphate concentration. Sample preservation. To prevent changes in phosphate concentration before analysis, it is important to properly preserve the samples. Preservation methods may include acidification to a pH level 2 with a suitable acid, that is sulfuric acid, to prevent microbial degradation of phosphates. Analytical technique. Calorimetric method. Phosphate ion can be quantified using calorimetric method such as molybdenum blue method. In this method, phosphate reacts with ammonium molybdate and antimony potassium tartarate in an acidic solution to form a blue complex, the intensity of which is proportional to the phosphate concentration. Ion chromatography. Ion chromatography can also be used for quantitative analysis of phosphate ion in textile effluent. UV visible spectrophotometry. UV visible spectrophotometry can be employed for phosphate analysis based on its absorbance at specific wavelength. Quality control. Implement quality control measures to ensure the accuracy and reliability of the analysis. This may involve using certified reference material running blank samples and performing calibration checks. Data analysis: analyze the phosphate concentration in the textile effluent samples. Results are typically reported in units such as milligram per liter or ppm. All of them are actually reported in milligram per liter or ppm. Compare the results to relevant regulatory standards or guidelines to assess compliance. Interpretation and reporting: evaluate the environmental implications of the phosphate levels in textile effluent. High phosphate concentrations can contribute to eutrophication, algal bloom and other ecological issues. Recommendation for mitigation or treatment may be included in the report, wherever required of course. Regulatory compliance: ensure compliance with regulation governing phosphate discharge in water bodies. Textile manufacturers may be subject to limits on phosphate levels in their effluent, and non-compliance could result in fines and other penalties. Overall, the analysis of phosphate levels in textile effluent is essential for environmental monitoring and ensuring the sustainability of textile manufacturing processes. Implementing effective wastewater treatment technologies can help reduce phosphate discharge and minimize environmental impact. So, by doing so, we can actually find mitigation methods and can effectively have wastewater technologies planned out in that manner, and therefore, it will minimize the environmental impact eventually. Now, let us see how total suspended solids are analyzed. Analyzing total suspended solids TSS in textile effluent is critical for assessing the levels of particulate matter present in the wastewater. Here is a structured approach for conducting such an analysis. Sample collection: begin by collecting representative samples of the textile effluent. Samples should be taken from various points in the effluent discharge process to account for any variations in TSS concentration. Sample preservation: to prevent settling or decomposition of suspended solids before analysis, it is important to preserve the sample properly. This typically involves keeping the samples refrigerated and analyzing them as soon as possible after collection. So, ideally they should be analyzed immediately, but if it is not possible, they should be kept under refrigeration. Analytical method: gravimetric analysis. Gravimetric analysis is the most common method for determining TSS. In this method, a known volume of the effluent sample is filtered through a pre-weighed filter paper. So, first the filter paper is weighed, then the sample is filtered, and then the filter paper is dried and weighed again. The filter paper with the trapped solid is then dried and re-weighed. The difference in weight before and after filtration represents the total suspended solids content. Turbidity measurement: turbidity can also be used as an indirect measure of TSS concentration. Turbidity meters measure the scattering of light by suspended particles in the effluent, with higher turbidity values indicating higher TSS levels. So, turbidity measurement is more qualitative rather than quantitative. Microscopic analysis: in some cases, microscopic analysis may be used to identify and quantify specific types of suspended solids present in the effluent. Quality control. Implement quality control measures to ensure the accuracy and reliability of the analysis. This may include using standardized filtration equipment, performing blank tests with distilled water and verifying the calibration of turbidity meters. Data analysis. Calculate the TSS concentration in the textile samples based on the results obtained from the analytical method used. TS concentrations are typically reported in units such as milligram per liter or ppm. Interpretation and reporting. Evaluate the environmental implications of TSS in textile effluent. High TSS concentrations can negatively impact aquatic ecosystems by reducing light penetration, smoothing benthic habitats and carrying pollutants. Recommendation for mitigation or treatment may be included in the analysis report if they are found to be high, not otherwise. Regulatory compliance. Ensure compliance with regulation governing TSS discharge into water bodies. Textile manufacturers may be subject to limits of TSS levels in their effluent, and non-compliance could result in fines or other penalties. By following these steps, the analysis of TSS in textile effluent can provide valuable insights into the environmental impact of textile manufacturing processes and help guide efforts to minimize pollution and promote sustainability. So, you see that this process of analysis is all directed towards one major factor, and that factor is how to mitigate or how to plan a mitigation strategy for removal of that particular substance. Analysis of cyanide. Analysis of cyanide levels in textile effluent is crucial due to its highly toxic nature of cyanide and its potential environmental and human health impacts. Here is a structured approach to conducting such an analysis. Sample collection. Start by collecting representative sample of textile effluent. This is a universal rule. Samples should be taken from various points in the effluent discharge process to capture any variation in cyanide concentration. Sample preservation. Since cyanide can degrade rapidly, it is essential to preserve the sample properly to prevent any changes in the concentration before analysis. Representation or preservation methods may include adding a sample or a chemical stabilizer such as sodium hydroxide or sodium carbonate to raise the pH and inhibit cyanide breakdown. So, cyanide first and the foremost thing is very crucial, and it has immense negative impact on not only the environment, but also human being. So, it is a very sensitive and highly toxic inorganic pollutant, and it is also not very stable. So, the sample should be either analyzed immediately, or if it has to be preserved, then certain amount of sodium hydroxide or sodium carbonate should be added, so that the pH becomes alkaline, and then it can be stored for some time before analysis of the cyanide. Analytical technique. Calorimetric method. Cyanide ions can be quantified using calorimetric method such as silver nitrate titration method or pyridine barbituric acid method. In this method, cyanide reacts with the specific reagents to form colored complex, the intensity of which is proportional to the cyanide concentration. Because it is a simple phenomena, if there is a reagent which specifically reacts with one ingredient and forms a complex, then that complexation can only take place with that ingredient. So, it is directly proportional to how much of that ingredient is actually present, and this is a very straightforward colorimetric analysis. Ion chromatography. Ion chromatography can also be used for quantitative analysis of cyanide ions in textile effluent. Electrochemical methods. Cyanide can be detected and quantified using electrochemical techniques such as amperometry or potentiometry. Qualitative control or quality control. Implement quality control measurements to ensure the accuracy and reliability of the analysis. This may involve using certified reference materials, performing blank tests and verifying the calibration of analytical instrument, because it is very important that the instrument is well calibrated, and we have just seen and also understood the importance of calibration of each instrument before the analysis. Data analysis. Analyze the cyanide concentrations in the textile effluent samples based on the results obtained from the chosen analytical method. Cyanide concentrations are typically reported in units again as milligram per liter or ppm. Interpretation and reporting. Evaluate the environmental implications of the cyanide level in textile effluents. Cyanide is highly toxic to aquatic life and can pose significant risk to even human health if released into the environment. Therefore, recommendations for mitigation or treatment may be included in the analysis report if the values are high. Regulatory compliance. Ensure compliance with regulations governing cyanide discharge into water bodies. Textile manufacturers may be subject to strict limits on cyanide levels in their effluent, and non-compliance could result in severe penalties. By following these steps, the analysis of cyanide levels in textile effluent can provide valuable information for assessing and mitigating the environmental impact of the textile manufacturing processes, helping to protect both the ecosystem and the human health. Now, let us see how anions and cations in the textile effluent are analyzed. Analyzing both anion and cations in textile effluent is essential for understanding the overall composition and potential environmental impact of the wastewater. Here is a structured approach to conducting such an analysis. Sample collection. Collect representative sample of the textile effluent from different points of discharge process. Ensure proper labeling and handling to prevent contamination. So, there is a test sample collection protocol even in this test methods. Everywhere the sample collection should be done in proper, organized and methods that have been described. Sample preservation. To prevent changes in the concentration of ions before analysis, it is crucial to preserve samples properly. Preservation methods may include acidification to a lower pH to prevent precipitation of cations or by addition of chelating agents to prevent precipitation of metal ions. So, preservations also are very specific to the kind of pollutant that needs to be preserved if the analysis is not done immediately. It may be required to lower the pH by using some acid, or it may be required that some addition of chelating agent may have to be added before it can prevent the precipitation of the metal ion. So, analytical methods that are used for the analysis of anion and cations are ion chromatography. Ion chromatography is powerful technique for the simultaneous analysis of both anions and cations in a single sample. It separates ion based on their charge and size, allowing for the quantification of various ions present in the effluent. So, the beauty is that from the same sample, using the same ion chromatographic method, both anion and cation can be analyzed simultaneously. Inductively coupled plasma mass spectrometry ICP-MS can be used to analyze cations such as heavy metals, copper, zinc, lead, cadmium, mercury at trace levels in textile effluent. So, ICP-MS is a very sensitive instrument which can analyze quantities even present in trace quantities such as ppm and ppb level, parts per million or parts per billion. Calorimetric methods. Specific calorimetric methods can be employed for the quantification of individual ions such as chloride, sulphate, nitrate and phosphate. So, this method is also very useful for anion and cation. Ion selection electrodes ISE can be used for direct measurement of specific ions such as fluoride, chloride, nitrates, etc. So, whether we are using any of these or all of them to verify if the contents are high is also possible, depending on the fact that they are available in the laboratory. Quality control. Implement quality control measures to ensure the accuracy and reliability of the analysis. This may include using certified reference material, running blank samples and verifying calibration of the instrument. And time and again we have been talking about calibration. Why is calibration so important? Because if we analyze an uncalibrated instrument, it is possible that it may give erratic result. If we do a blank run, if we do a reference run, then we are assured that the instrument is working properly, and therefore, the unknown sample which has been collected and which has been brought for analysis would be expecting to give correct result. Data analysis. Analyze the concentration of anion and cation in the textile effluent samples based on the results obtained from the analytical methods used. Concentrations are typically reported in units such as milligram per ppm. So, everywhere all these inorganic pollutants are reported in terms of milligram per liter or parts per million, that is ppm. Interpretation and reporting. Evaluate the environmental implications of the anion and cation levels in textile effluent. high concentration of certain ions, particularly heavy metals, can have detrimental effect on aquatic ecosystems and human health. Recommendations for mitigation and treatment may be included in the analytical report. Therefore, it is important that these analyses are done in a very accurate manner. Emphasis on accuracy and calibrated machine and the analysis to be carried out on these calibrated machines is repeatedly emphasized. Why? Because these values are very crucial. If they are high, then the mitigation plan has to be accordingly designed. If the values are low, then another kind of mitigation plan can be planned out. But if the values are really very low, then there is no need for any mitigation plan to be made. Regulatory compliance. Ensure compliance with regulation governing the discharge of anion and cations. Discharge of anion and cations into water bodies. Textile manufacturers may be subject to limits on specific ions in their effluent, and non-compliance could lead to regulatory penalties. By following these steps, the analysis of anion and cations in the textile effluents can provide valuable information for assessing and mitigating the environmental impact of textile manufacturing processes, helping to protect water quality and ecosystem health. Because after all, we have to be responsible for preventing the ecosystem and in turn even preventing our health. Planet is one place which has to be kept safe for all the vertebrates, invertebrates, including human being. The analysis of inorganic pollutants, therefore, to conclude, in textile effluent is a critical component of environmental monitoring and regulation in the textile industry. Through comprehensive analysis, including the assessment of ions such as chloride, sulphate, ammonia, nitrate, phosphate, cyanide and heavy metals, the potential environmental impact of textile manufacturing processes can be evaluated. And it is also important that we analyze the TSS and the TDS. The findings of such analysis provide valuable insights into the composition of the textile effluent and their potential effects on aquatic ecosystems, human health and overall environmental quality. Because why are we doing this exercise? We are doing this exercise in order to assess the inorganic pollutants that are present. Only when we know the analytical results of each of these parameters, that is ammonia, sulphate, chloride, nitrate, phosphate, cyanide and heavy metal content in the effluent, we will be able to know whether or not this water should be discharged into the water bodies. We would be able to know whether we should do some strict mitigation plan or we can do some easy mitigation plan, or we do not need any mitigation plan. In conclusion, the analysis of inorganic pollutants in textile effluent plays a vital role in environmental stewardship and sustainable manufacturing practices. By understanding the composition and impact of inorganic pollutants, textile manufacturers can work towards minimizing their environmental footprint and safeguarding water resources for future generation. So, if we have to adapt sustainable approaches, we need to be concerned about the environmental impact of these pollutants. We have seen about the organic pollutants, and now in this lecture we learnt about the analysis of inorganic pollutants. By understanding these, we understand the seriousness of these pollutants and their presence in textile effluent and the need for mitigation, as well as to make the water bodies or to remain the water bodies safe, so that the aquatic ecolife or ecosystems are restored and they are not harmed, neither the human health is harmed. With this, we have come to an end of this lecture. Thank you.